So how are rational tangles algebra? That is, how does the way in which we construct rational tangles fit into our ideas of what makes a group in abstract algebra? I think we can convince ourselves that the closure property will hold for rational tangles, because any tangle move that creates for me one rational tangle into a new rational tangle, by definition just makes more rational tangles for me. So if I just further tangle up any rational tangle using our tangle moves, the result is again another rational tangle, just by definition. Also, I think we can convince ourselves that the empty tangle, no twists at all, strands arranged horizontally, is like an identity element for us. So the real interesting question is about inverses. And that, in the language of tangles, is how do we untangle a tangle using only the same types of moves that were used to create it in the first place? If I go out in the wild and I catch me a rational tangle and I pin it down like some sort of butterfly, right? How can I then apply rational tangle moves, in other words, twists, rotations, to that rational tangle in a way that's going to untangle the whole thing and return it to an empty tangle? How is that possible? That's the question that we begin to explore in this next activity with some quite surprising results. The first observation is that, in fact, after the previous activity that we did, we know that any rational tangle can be untangled because you know how to untangle, how to undo each of the fundamental tangle moves, the generators that make up our tangle group. We know how to undo a rotation using more rotations. We know how to undo a twist using more combinations of rotations and twists, right? So we can undo each one of our tangle moves. And fortunately for us, that means that we can untangle any tangle, that we at least have some process for doing so. We can untangle a tangle by using the inverses of each of those generators to undo each of the moves, each of the letters that make up our tangle word in succession. So what does that look like? Let's suppose I start with a tangle that has the word, the recipe, t, r, t to the third power. So I'm going to twist this, then I'm going to rotate it, then I'm going to twist it 3 more times, and that'll be my tangle. And after I've made that tangle, this is what it ends up looking like. If you make this tangle yourself, by the way, you might already spot a shortcut just in watching how the strands work. But if we take the naive approach, right, the one that we know will always give us an answer, we can invert this tangle just by inverting each one of the moves that we just did to create the tangle. And the algebraic principle that we need to do that is called the shoes and socks theorem. The shoes and socks theorem is just a reminder to us that the first move that we want to undo is the last move that we had to do to create my tangle. It's like when you're unwrapping a Christmas present that has a bunch of layers of paper on the outside. The first layer that we unwrap was the last layer that was wrapped. Right, so we work from the outside back in. Algebraically, what that means is if I want to undo t, r, t to the third power, or if we rewrite it t, r, t, 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 the first thing I should undo is this last t that we did. But we know, after the last activity, how to undo a single twist through a combination of other rotations and twists. So if I apply that combination, I'm going to cancel out this last t in my word. And my word will then be trtt. What would I do next? Working again from the outside to the in, we cancel the next innermost t using the same inverse. We cancel the next innermost t using the same inverse. Now my word is just tr, everything else is canceled. So now I need to cancel the r. We know how to cancel the r. Then my word is t, and I can cancel the t using the combination of t's and r's that we know is the inverse of t. So we can build an inverse for my tangle that we call G, right? And this will work. The question, though, is that the only way? Could I have done this in some other fashion? After all, when we did the rational tangle dance example, the inverse that we wound up with was a lot shorter than we would have otherwise expected it to be based on gluing together the inverses of each generator using the shoes and socks principle. So really the question is there a more efficient way to invert a rational tangle, to untangle it? Is there a shorter word that I could use to represent the inverse of this tangle? We know that inverses are unique in any group. So it's not as though we're writing down a different inverse, just a different way to express the inverse, hopefully using a shorter number of words, a shorter number of letters. The way we're going to look for a more efficient inverse is by trying to uncover what I call the mystery of the tangle dance invariant. In other words, what we're going to ultimately do is find a better way to represent rational tangles besides just spelling out the word. Because it seems to be the fact that we're using these letters T and R to represent them, and then trying to invert each letter one at a time, that's causing our inverses to be as long and complicated as this one seems to be. So if we can find a different way of representing tangles, maybe that will also lend itself to a better way, a more efficient way to invert tangles. And by using that invariant, I'll be able to find out that there is in fact a simpler expression for this inverse. That just doing RT squared should also give us an inverse for this tangle, but we might not have expected that the tangle RT squared and the tangle represented by this giant slew right here, they're both the inverses to G, and therefore they are both the same object in the rational tangle group. But we might not have otherwise known that. And just to verify, let's see if when I try to apply this inverse to TRT cubed, that it actually does untangle the tangle. So here I have my original tangle, G, TR, T cubed. All my twists are inside of this envelope. And according to this new supposed recipe for my inverse, the first thing I ought to do is rotate. The second thing I ought to do is apply a twist. So I'll take my northeast corner and I'll move it over my southeast corner. Reattach those endpoints, like so. So now I have this new twist over here on this side. Then I'm supposed to rotate again. And then I'm supposed to do 2 more twists. That's my T squared here on the end. So I'll take the top northeast, I'll bring it over the southeast. My strings are getting kind of short to do this. I need to do it one more time and then reattach. There we go. So I don't quite have a square anymore because my strings are getting too close. So what I have now is a tangle whose word would be TRT cubed, followed by RT squared. And if this actually worked, then we should have a fully untangled rational tangle at the end of this process. And of course, this is the fun part of the magic trick, where we free the tangle from its envelope. And we find out that indeed all my crossings are undone, right? And I have my empty tangle again. So why is this surprising? It's surprising because the inverse that we just found had only really 5 steps in it, right? A rotation, a twist, a rotation, and 2 more twists. When the inverse that we found just generator by generator, 1 letter at a time, had, what is this, 5, 10, 15, 21 steps involved. And yet both of those represented the inverse of the same tangle, and therefore they represent the same element. So how could we have known about this shorter inverse? How did I discover this shorter inverse in making this video? I did it by coming up with a better way of representing rational tangles. Instead of using words built out of these letters T and R, and those words can be very, very long and actually not very illuminating, what we want to find is a better object to represent tangles with. Better than words. Specifically, if I can find a kind of object that also has an arithmetic or algebraic structure to it, we're going to find that rational tangles can be adequately represented by rational numbers, which is where rational tangles get their name. And they can be represented in such a way that you can tell me exactly what rational tangle that you're talking about simply by giving me a single rational number. And if that completely tells the story of rational tangles, it can also completely tell the story for how to untangle a rational tangle. And the way in which it tells that story is how we can decide on very often a more efficient way of inverting a rational tangle, untangling a tangle that's more efficient than just doing it 1 generator at a time. And that's the search that we're engaged in for the rest of this chapter.